estimation of pi, but we figured also that people wouldn't be around Friday afternoon. And I would be one of those people that's not going to be around Friday afternoon. So that's why I wanted to do it a day early. So pi activities and the UC from 11 to 1, and then honest to goodness pi at 1:30, from 1:30 to 3. So come eat pi. Questions about anything? Things are going okay? All right, so last time we talked about the Poisson distribution. Do we remember what the PMF for a Poisson distribution looks like for a general lambda? Good. That's our PMF for, pardon me, any Poisson distribution. So the lambda is the parameter that's given to us, or we have to figure out one or the other. X then is the number of occurrences during a given interval. That interval may be a time interval. It may be some of the examples they do in the book are like you do a roll of tape or a roll of metal or what have you, and maybe you're looking at the number of occurrences of a flaw in a certain number of feet or meters or what have you. But again, there's some interval that we're considering as a unit interval. It doesn't have to be a length 1 necessarily, but we're considering whatever the interval is a unit interval. And then lambda represents the mean number of occurrences that happen during that interval. Okay. So x is what's counting that. Lambda is the mean number of that. So remember that our mean and our variance for a Poisson distribution is that lambda. And then our moment generating function was what? E to the lambda times e to the t minus 1. We collected all of those things at the beginning, well, somewhere around the beginning of class last time. And then we started talking about what we need to do to solve the problems. So let's look at this next problem in the packet. Here we've got a Poisson distribution. They tell us what the lambda is. And it's asking us the probability of being greater than 2 given that x is less than or equal to 4. So one of the reasons why I wanted to do this one, just to remind us of conditional probability. How do we do conditional again? Yeah, probability of intersection. And then divided by. Say it again. Yeah, it's the given part, right? The probability that x is less than or equal to 4 in this specific case, but generally speaking, it's the probability of the intersection over the probability of the given, right? Okay. So I've written the top, the intersection part, as the probability that x is greater than or equal to 2 and less than or equal to 4. What x value satisfies that? 2, 3, and 4. Good. So really, we didn't want the probability when x is 2, when x is 3, when x is 4. I'll just write it as that. So I have probability that x is less than or equal to 4. Now again, later on, and starting pretty quickly, because I believe we should get to continuous distributions today. When we deal with conditional, try that again. When we deal with continuous distributions, rather than adding things up, we will integrate to get our probabilities. And a lot of times, if we integrate a general function, we'll have what we call the cumulative distribution function, and you just plug numbers into that to give us our probabilities up until a certain point. So to help start practicing that, if I use capital F to denote the cumulative distribution, how would you rewrite the denominator in terms of the cumulative distribution using capital F as the function name? It's just f of 4, right? Because remember, your cumulative distribution is the probability that x is less than or equal to some little x, right? That's what the cumulative distribution function is. It accumulates probability from whatever your lowest value is in your sample space up until a certain point. That's why we call it cumulative. Can you do the same thing for the numerator? Can you express it in terms of the cumulative distribution? What would we write for the numerator?
F of 4 minus, and then it'd be 1 minus F of 1.
I don't think you went with the 1 minus part. You're doing the right thing. I think I just want the f of 1, right? Okay. So this would be, that part right there is just the probability that, let me write it in red so I'm not going black everywhere. This part right here is the probability that x is less than or equal to 4. What does that include for x? What values of x does that include? 0 to 4, right? What ones don't we want? 0 and 1. So we're going to subtract those off, which is what that particular probability gives you. Now, this is true in the discrete case. In the continuous case, we would have just used f of 2 here because the intervals would have butted up right next to each other. We'll talk more about that when we actually get to it. But I just wanted to do this a little bit with a practice of writing in terms of the cumulative distribution function, because we're going to do that a lot when we get to continuous distributions. Is that okay? If you did probability of x equals 4, then you would just put in the PDF, the PMF, and just calculate it. We only use the f when we're talking about intervals, yeah. Intervals of things, the capital F. We could have also written these as summations, right? Another thing you could have done was, I'm just trying to illustrate different things that we could do, right? The denominator here would be the sum from 0 to 4 of 1 to the x. Well, that's just 1. So you'd have e to the negative 1 over x factorial. On the top would be sum from x equals 2 to 4 of the same expression. Anything going to cancel? E to the negative 1s will cancel, won't they? Notice there aren't any x's in the e to the negative 1s, so you can factor them out in front of your sums and then cancel them. So if you were to write this out, the numerator would be a half plus a sixth plus a 24th. The denominator would be 1 plus a half plus a sixth plus a 24th. Then you can calculate it, yes. Say that again. What's lambda in this case? What's lambda? Just the lambda value is what? 1. So if I put lambda equal to 1 here, what do I get there? Just 1. Yeah, that's why it's just e to the negative 1 over x factorial. Yep. This okay? All right. So again, it's just a matter of which way you want to do it. I'm only referring to the cumulative distribution. Well, there's 2 reasons why. I'm only referring to the cumulative distribution because 1, we're going to do that a lot when we do continuous distributions. Okay. 2, you have those functions built in your calculator or Excel. So if you're actually just trying to get a numeric answer, you would use those functions rather than have to type all this stuff in your calculator. Right? That would take a little bit longer, wouldn't it? All right. All right, let's do the next one, since everybody's so excited about these problems. Okay. This reason why I put this problem on here is it illustrates the idea of the independence of a Poisson process. So let's talk a little bit about what I mean about that. We've got some aluminum screen has one flaw per 100-foot roll, but then asks you something about a probability of a 50-foot roll having no flaws. So notice that we changed the interval, right? The interval was 100. Now it's 50. Okay. So relative to the original, how big is that one? Half of it, right? So if you expect one flaw for 100 feet, how many flaws would you expect in 50 feet? Half of one, right? So that's the scaling part, right? That's the idea of it all being independent. Remember when we said we had an approximate Poisson process, we could chop it up into little pieces where they were all independent. So all we're doing here is just saying that, again, if you expect a certain number in one length interval, you can scale it to any other length interval. So if this were a 300-foot roll, what would you use for lambda? 3, right? If it were a 25-foot roll, you would use a fourth, yeah. So you just scale it appropriately depending on whatever was the original unit given to you. And in this case, what I mean by a unit is the 100-foot roll. So we can scale it appropriately. So since we're doing a 50-foot roll, our lambda will be 1/2. Because again, if it were a 100-foot roll, the lambda would have been 1. We want no flaws, so we want the probability that x is equal to 0. I want to write it out longhand, but we know our lambda is 1/2, so we'd have 1/2 to the 0 over 0 factorial times e to the negative 1/2. But 1/2 to the 0 is equal to 1, and 0 factorial is equal to 1. So this just turned, whoa, shifted on me. So it's just equal to e to the 1/2. The end. Bless you. Yes. For this one? Oh. Mm-hmm. Yep. We could if we had a nice formula for it. We don't have a nice formula for it in terms of the Poisson. We will, again, I'm just doing this as a preview for what we're going to do for continuous distributions. And in the continuous distributions, we'll have some nice forms for them. Okay. For this one, we don't really have any nice forms, unfortunately, yet. But, pardon me, but it's a good preview for what we're going to do later. Okay. All right. Let's look at the next one here. Traffic accidents in a city says, I think it has a weekly mean of 3, and it asks for the probability of exactly 2 accidents in 2 weeks, right? Oh, I remember correct. What lambda are you going to use to be able to answer this problem? 6, right? Because notice that the mean they give you is for a 1-week period, right? And we have to scale it. So since we're scaling it to 2 weeks, that tells us that our lambda is going to be 3 times 2, right? We're scaling it to a twice as long time period, a twice as long interval. I know I said time period. I'm trying to get away from just time period. It's an interval, right? The original interval they gave us was 1 week. We scale the interval up by 2. So that scales your lambda by the same amount. Okay. We want exactly 2 accidents in 2 weeks. What would we get in that case?
6 squared over 3 factorial times e to the negative 6.
Good. So your lambda is 6. So you get lambda to the x, so lambda squared over x factorial, so the 2 factorial, e to the minus lambda, so the negative 6 there. What is that? 18 e to the 6th? Or e to the negative 6, I mean. And if you really want a decimal approximation, that's what you put in your calculator. What questions do you have on that one? Again, these two examples are on here in particular because of this scaling idea, making sure that we're all on the same page with the scaling. Yes? Well, there can't be really a given part because there's no probability with it being a 2-week time period. So the given part would have to be some event. The event here that we're talking about is counting accidents, right? So the weeks part here isn't a given part. It is a given interval, but it's not a given in terms of the probability. Okay. All right. Any other questions on that one? Let's do another one here. Work on that one for a minute, and then we'll talk about it. Pardon me. Bless you again. Ready to chat? All right, what'd you do? Okay. Why is it 3?
Because you got 30 seconds is the new interval.
Good. So the original interval was 10 seconds. It went up to half a minute or 30 seconds, so it's 3 times as long. So we do 3 times the lambda. Okay. What's next? Okay. Probability that x is less than or equal to 1, isn't it? It says more than 1. It doesn't include the 1. Right? This is more than 1, so it doesn't include 1. How will we do the probability that x is less than or equal to 1? Good. Yep. Probability that x is 0 and x is 1 plus x equals 1. Try that again. Probability that x is equal to 0 plus the probability that x is equal to 1. What do you get for probability that x is equal to 0? Okay. And what do you get for the probability that x is equal to 1? Good. So we should get 1 minus 4e to the negative 3 when we're done. The coefficient on this first part is 3 to the 0 over 0 factorial, so that's just 1. The coefficient on this part is 3 to the first over 1 factorial, which is 3. Is okay? Are we okay with the scaling, or do you want to see one more? You want to do one more? Okay. All right. Let's do one more. Let's do the next one. Work on the next one for a minute. Although I'm not sure the next one's much different, but go right ahead and do the next one. Bless you. Not that it necessarily matters for anybody in the room, but if you're interested in taking the probability exam for actuarials, for actuaries, called exam P, there's 30 problems on this is a sample problem. There's 30 problems on it, and it's 3 hours, so you have to be able to do problems on an average of 1 every 6 minutes ish. So, just as a time gauge kind of thing for these. You don't have to get them all right necessarily to pass. And if you're interested in such a thing, literally all they expect you to do is pass. Employers, I mean, they just want you to pass. They don't care if it's perfect. A lot of employers will say, well, they have a cut score, which is referred to as they have a 6 or higher as passing, and they basically say if you got higher than a 6, you studied too long. So, all right, ready to talk about this one? All right, what did you do first? Lambda equals 6. Good. All right. Because you've scaled up from the 1 week period to the 3 week period. We want probability that x is less than 4, because it says fewer than 4, right? So what we need to calculate for that? Good. Again, if we had a nice CDF, nice cumulative distribution function, you could have just plugged in 3, right? If we would have had a nice closed form for that, basically it is just a summation, so there's not a lot of call for doing it right now. Like I said, it's something that would be better for continuous distributions, but you could have written that in terms of a cumulative distribution function as well. What did you get for the probability that x is equal to 0? And then for 1, and then for 2, and finally for 3. Okay. 6 to the 0 over 0 factorial, 6 to the first over 1 factorial, 6 squared over 2 factorial, 6 cubed over 3 factorial. Those where the 1, 6, 18, 36 are coming from. What is that? 61? Did I add it right? Okay. Is this okay? Any questions on that at all? Feeling fairly comfortable with the Poisson problems? Yeah, okay. The mutually independent tells us the fact that we can scale it up to a 6. That's what the mutually independent tells us, is that we can scale up to the 6. That's what allows us to scale it. All right, I'll leave the last one for you for practice because it's essentially the same problem, right? The last two were essentially the same problem, weren't they? Okay, all right. Okay.
Why do you do just all the probabilities add up instead of doing the 1 minus probability of all those add up?
Well, if it was 1 minus, I would be doing the complement of something, right? So if I'm doing 1 minus, the complement would be greater than or equal to 4. So then I would do 4 or 5 or 6 or 7 or 8 or so on. This is set up exactly to do 0 or 1 or 2 or 3 to satisfy that. That's why we don't have the complement. Other questions at all? All right. Pardon me. Let's go on to the next section then, which talks about continuous distributions versus discrete distributions. So we're going to start our continuous distributions, much like what we did for discrete distributions. We will build up some special continuous distributions as well. If you still have that purple sheet, the continuous distributions are on the back side of the discrete ones. All right. So when we had some things that might be examples of doing something that are continuous distributions would be maybe goodness gracious, right? Heights of people, because heights are infinitely divisible. Time until something occurs. Time is infinitely divisible, right? So you can think of scenarios where you've got probabilities of something happening, but it's measured in a continuous fashion rather than just a single occurrence or 2 occurrences or 3 occurrences, because you can't have a half of an occurrence, for example, right? Or we did successes, right? Well, you can't have half of a success or 2/3 of a success. So for continuous distributions, then, we need to talk about how are we going to do our probabilities. So we do our probabilities with what are referred to as probability density functions. And this is the continuous version of probability mass functions. Okay. So much like our probability mass functions, it doesn't make sense for a density function to be negative. So one of the properties that we have to have, and I'm going to use f of x to denote our PDF, little f of x. We need to make sure that our density function is greater than or equal to 0 all of the time. We don't want to have any negative density. A negative density would imply that you had a negative chance of something happening. Which makes no sense. Even though people say that, right? There's a less than 0 chance that I do that. All right. The second part is that if I integrate over the entire sample space, and this is the notation that we're going to use for that. This just says I'm going to integrate over whatever the sample space is. If I integrate over the entire sample space, I better get 1. This basically says that the probability that the sample space happens, something in the sample space happens, is 1. Okay. And the last part is if A is a subset of S, then the probability that our x is in A is the integral over that set of the function. Let's think about why this is the continuous extension of a discrete probability mass function. So integration here, this is just adding everything up, right? And we know that when we add up all the probabilities of things in our sample space in a discrete distribution, we have to get 1. This is just the continuous version of that, right? It's just adding up everything in the sample space. Think about how you first defined doing integration. The first thing you did was what? You chopped up your interval into discrete pieces and then added them up, right? So that's exactly what we're doing here. We're just chopping up the interval into discrete pieces, adding it up, and saying that gives us an approximation. Take the limit, you get the interval. So same concept here. The last part, remember, said that if we had a set and I wanted to know what the probability that x was in the set, then I could just go in each element of my set, plug it in, and calculate the probabilities and add them up, right? Well, again, we have a continuous function. Adding up is doing an integral. Same idea. So this is what we mean by a probability density function. If, just to put something next to item number 1 here, if your x is not in the sample space, then we're automatically going to get 0 when we plug it into the probability density function. The only way that your probability density function can be non-zero is if you're in the sample space. Does that make sense? What this does is it allows us to define the probability density function over the entire real line if we want to, rather than just on a particular interval, even though we'll only ever care about the interval. All right, so let's see if we can use these properties and do some problems here in number, the first example that I have on your sheet here. So the first problem here gives you a function, 2 times 1 minus x, but only from the interval from 0 to 1, and everywhere else it's 0. So really all we care about is this interval from 0 to 1. The first part asks you to sketch the graph. What kind of a function is this? It's a line, right? Notice it, if you put it in 0, you get 2. If you put in 1, you'll get 0. My scale's goofy, but and I really didn't divide my y-axis in half either, but that's what we would get, right? Now again, this is going to stop right here, right? And it's going to stop right there. I don't care about anything else. I'm going to do part C first before we do part B. But let's just talk about why we know that this is a PDF. Probability density function, PDF. We'll use the third property to calculate the probability, so let's just concentrate on the first two. On the interval that we're talking about, is the function non-negative? On the interval from 0 to 1, is the function non-negative? That's good. The second part is does the function integrate to 1 over the interval? Well, what was your first interpretation of the definite integral back in calculus? Area, right? What's the area of that triangle? It's 1, isn't it? 1/2 base times height, we get 1. Okay. So this is something that you might want to make sure that you're thinking of as you're going through problems. If you've got a region that's areas that you know how to compute, you can do your integrals that way. You don't have to actually, honest to goodness, integrate the function. Okay? If you can recognize what the area is that you're talking about, then you can just write that down for the probability. Okay? So let's see if we can use that idea to do these 4 parts. Okay? Probability that x is between 0 and 1/2, right? So we're talking about that area right there, right? That's the probability that x is going to be between 0 and 1/2. There's a couple of ways to think about getting that area. One, I recognize that as a trapezoid, right? So I could calculate the area of the trapezoid. I don't feel like calculating the area of a trapezoid, but you can, okay? Do you see another way that might be a little bit faster to get at? Well, yeah, I could make a triangle time. I could do, but can I calculate that area fast? Yeah, what is the area of that piece? A fourth, isn't it? Or is it it's a fourth because it's that height is 1, right? And the base is 1/2. So the area here is 1/4. So what's the probability that we want? Yeah, 1 minus 1/4. Good. Just like in discrete problems, sometimes it's helpful to think about the complement. You could have done it the other way. You could have divided it into a triangle and a rectangle, right? This triangle up here has area 1/4, and that rectangle there has area 1/2. And added it together. Or we could have integrated it, right? Let's just make sure that we really are getting the same answer, even though we should be. If we do the integral from 0 to 1/2, there's also a couple of ways that you can integrate this. Probably the easiest way to integrate it is just treat the 1 minus x like it's the variable. Do a u substitution idea. Because if I let u equal 1 minus x, du is just negative dx, right? What's an antiderivative for 2u? U squared, so we get negative 1 minus x quantity squared from 0 to 1/2. I need the negative to adjust for the negative on the x. And I get 3/4 that way too. You could have also pulled the 2 out and integrated piece by piece. You get the same answer. You could have distributed the 2 and integrated piece by piece and get the same answer. Okay. One thing, this is just my personal preference. You don't have to do this at all. One thing that I like to be used to is when I have a negative out in front. Do you remember what the negative does to the limits of integration? Flips them, right? So if I say a negative out in front, I just plug in the bottom and then subtract what I get when I plug out the top. I can just flip it. I just do it in my mind that way. So if I say a negative in front, I just do bottom minus the top. which is what I did here. It's just little tricks. Again, if you're thinking about anything that involves test taking ideas, anything you can do to save time, that saves a little bit of time. You don't have to do that at all. All right. Let's skip 2 for a second. We'll come back to 2. Let's do 3. What's the probability that x is actually equal to 3/4? Okay, so remember that according to being a PMF, I have to be able to calculate the probability through integration, right? So if I think about it as an integral, that would be the integral from 3/4 to 3/4. So what would the integral be? 0, right? So your probability that you're actually equal to anything ever is always going to be 0, okay? Always 0. It's the same idea because what you're thinking of is the property from calculus. If I go from A to A, I don't have any area, right? Same exact concept. Right. The last one we could do by looking at the same kind of picture here. I'm going to erase the red. If I put in 3/4, that's going to be at a height of a half. I didn't draw it very well. This should be a half, right? We agree? Because if I put in 3/4 there, I'll get 2 times 1/4. And so the probability that we're greater than 3/4 is that area. So you'd have a half times 1/4 times a half, right? Okay. So far, so good? Yes. Why did I do what? I didn't compare anything. I plugged 3/4 in to get a height of a half so I could calculate the area. Because I was just trying to find the area under the curve, right? So if I put 3/4 in for x up here, I get a half. So I only did that to get my height of my triangle. All right, I want to come back to 2, but let's answer part B. It says determine and sketch the graph of the distribution function. Okay. So so this is like your cumulative distribution function. So remember again, we talked about cumulative. If it just says distribution function, it means cumulative distribution function. I'll just use the letter CDF for that. By definition, your cumulative distribution function is the probability that your random variable is less than or equal to whatever the input is. So from an integration standpoint, my input goes in as my upper limit of integration. I'm using a negative infinity down here, but this is just really your lowest number that you could put in your sample space that gives you a non-zero value. So this looks like an improper integral, and we will do some improper integrals in here. I know you're very excited about that prospect. Basically, this is the portion of class that is, hey, do you remember Calc 2? We're going to do some integration by parts. We're going to do some improper integrals. In any event, even though I have a minus infinity here, you will not always use minus infinity. But you will always use the lowest value on your interval, on your support. What is the lowest value for x that we're allowing in this problem? 0, right? So for our purposes in this problem, our distribution function will be the integral from 0 to x of 1 minus t dt, 2 times 1 minus t dt. That's the lowest possible x value that we have in our support. Even though I wrote minus infinity, remember we said that if we're not in the support, if we're not in the sample space, then we assume it's 0. So all I'm doing is just deleting off the left-hand side because it's going to be 0 when we integrate it. Okay. We did this integral a minute ago. This was negative 1 minus t squared. Bless you, man. There's a lot of sneezing going on today. Bless you again. All right. And notice again, the minus sign here will flip your limits of integration. If we put in 0, we'll get a 1, right? And I put in an x, I get 1 minus x squared. We agree? All right. So this is the distribution function. The second part, the part B, try this again. The second part of part B asked you to graph it, right? It said find it and graph it. Okay. Kind of a graph is this? Parabola, right? And then it's going to, what's it going to do? Well, squaring this, I can think of it 1 minus x is the same thing as x minus 1, so it doesn't really matter. The open down, right? This one might actually help us a little bit if we actually multiply it out. If you were to multiply this out and rewrite it, you get, yeah, it should be negative, yeah, 2x minus x squared, yep. Okay. Now remember that this only is on the support though, right? Your support is from 0 to 1. Okay. One thing we notice, at least I hope we notice, this function would cross the x-axis at 0 and 2, right? That's pretty straightforward to see, isn't it? You just factor out an x. I hope you see that it crosses at 0 and 2. But we're not going to go all the way down to 2. We're only going to go to 1. It's at 0 at 0, and it's up at 1 at 1. You can check that pretty quickly. That's where it stops. So you have that part of the parabola. That's all we have. Now, as a technical piece, your cumulative distribution function actually has a domain negative infinity to infinity. On the left-hand side, of course, until you get to 0, you haven't accumulated any probability. So that would be 0 on that side. At this point, we've accumulated all possible probability, right? That's it. It's all the probability we get. So this would shoot off that direction as a horizontal line. That would actually technically be the graph of the function. Okay. If I were to write this out longhand, your cumulative distribution function looks like 0 for x less than 0. I can put the equal to on either spot. It's 2x minus x squared between 0 and 1, and it's 1 once we get past 1. It's the whole reason why it's called cumulative is because it's accumulating probability, right? We haven't until we get to 0, we don't accumulate probability. Once we get to 0, we start accumulating it, and it accumulates pretty fast, and then it tapers off. And then once we get to 1, it stops accumulating probability. We've accumulated everything, so then it's a horizontal line. Does that make sense? All right. So now that we have our CDF right here, let's see if we can use this to answer part 2 of part C. Okay. Part 2 of part C was find the probability that you're between 3/4 and 1/4. How can we express that with the CDF?
So 3/4 minus 1/4.
Good. Notice that we don't have to worry about jumping down a unit here, right? Because it's continuous, correct? Right? Really what we're doing here, this last piece right here, this second part, is we're subtracting everything at 1/4 and below. So technically we've got overlap, right? Because this should include 1/4. This is deleting out 1/4, right? You see what I'm saying? This says include 1/4. This says subtract out everything up till 1/4. So really I'm deleting out an overlap point. But do I need to worry about deleting out a single point? No, because the probability that you're actually equal to a single point is 0. So that's why it's okay to write it this way. Okay? So now we can just do our cumulative distribution function, 2 times 3/4 minus 3/4 squared, and then minus 2 times 1/4 minus 1/4 squared, whatever that turns out to be. Was it? 1/2? Thanks. I didn't really feel like doing it in my head. I'm sure it's 1/2. Yep. Is it okay? Yeah.
Is it always going to be the same as just doing the integral from?
Yes, that'll be the same as doing the integral from 1/4 to 3/4. Yep. Yeah, you can do it that way too. But since we already have the distribution function, we can just plug it in rather than having to do an integral. All right. Questions on that one at all? All right. So question 2 here on your handout is a lot like those problems that we did back in discrete probability distributions, where we had to figure out the constant that made it a PMF, right? Added up to 1. This one's asking us to find a constant that make it a PDF. So we're going to use that second property again to help us to figure out what the C has to be. And basically this is just asking us to set the integral equal to 1 and see what happens, right? So if we integrate for part A, if we integrate from 0 to C of x cubed over 4 dx, we need to get 1 when we're done, right? That was the second property of being a PDF. If I integrate the PDF over the entire sample space, we have to get 1. So that's the property we're using. It's the exact same property we use for PMFs, right? If we summed the PMF over the sample space, we had to get 1. Yep. Okay. Antiderivative for x cubed over 4?
X to the 4th over 16.
Good. Oops, oh, I have an equal sign over on that side. C to the 4th over 16 equals 1. So what does C have to be? 2. Good. part okay? You would do the same thing for B. I'm more interested in doing part C. I'll leave part B for you for practice. It's not hard. At least I hope it's not hard. If you can integrate x squared, it shouldn't be too difficult. All right, for part C, we're going to integrate from 0 to 1 of c over root x dx. And we want that to equal 1. Now, before I do anything, I want to discuss this integral and how we're going to handle integrals like it. All right. What's wrong? Not what's wrong. What's bad about this particular function? What can I not plug in? 0. I also can't plug in negatives, but I'm not being asked to, right? But I cannot plug in 0. Is 0 one of my limits? Or in my interval? Yeah. So remember what you had to do back in Calc 2 when you had a situation like that? We had to change it into a limit and do an improper integral and then take the limit at the end? Remember doing that? We're going to be super lazy and not do that. Okay? We should be able to tell whether the limit is going to exist or not at the end without having to write the limit all the way to the end. Okay? The reason for that is because remember what you did in Calc 2. What did you do? If the limit existed, you just plugged the number in. If the limit didn't exist, you couldn't just plug the number in, right? So we're just going to see what happens when we do it. Okay? So let's pull out the C. Right, this is x to the negative 1/2. Set that equal to 1. Antiderivative for x to the negative 1/2. 2x to the 1/2. Now, again, technically I should be writing this as a limit, right? I should replace my lower limit of integration with a variable. Let the variable go to 0 from the right. Do my antiderivative, then plug in the variable. But at that point, is there any problem with plugging in 0 into this number here? No, so then you just evaluate the limit by direct substitution, so why write all the limit stuff? Okay. Now, if you take it for Calc 2, you're going to be writing all the limit stuff, because that's really what we're doing, okay? But right now, we're doing probability problems. We're just trying to get to the answer at the end, okay? So do know that I'm glossing over concepts here. But you should have already learned those concepts. That's why I'm glossing over them. All right. So the right-hand side is just, try that again. The left-hand side is just 2 when I plug those in. Okay. The second part of the question says, is this PDF unbounded? Well, if you were to draw the PDF, your PDF should look like that, right? And have a vertical asymptote at 0. We agree? It'll stop at 1, but it'll have a vertical asymptote at 0. Okay. So is it bounded? Or does it go off to infinity? It goes off to infinity, right? So it's not bounded. That's what it's asking about. But you can still have PDFs that are not bounded as long as the integrals converge. Okay. Questions on that one at all? Is it okay? Yes. How did I come up with what? I just graphed this function. I know it has a vertical asymptote of 0. I just drew a rough sketch. I know that if I put closer and numbers that are closer and closer to 0, it gets really, really big. If I put in really big numbers, it should get really, really small. And technically, I shouldn't even have drawn the whole thing. I should have drawn it up to here and stopped it at 1, like that. That's where I should have stopped it. And even more technical, I probably should have put an open circle there because the 1's not included. I don't really care what happens at the endpoints, right? Because again, the probability of something at an endpoint is 0. At a particular point is 0, endpoint or not. Let's do the CDF for this one. We know what the constant is now. So if you wanted your CDF, I would do the integral from 0 to x of 2x to the negative 1/2. Not an x, 2t to the negative 1/2 dt. Why am I using a t now, by the way? Why didn't I write an x here? Because the x is up here. This variable has absolutely nothing to do with that variable, right? Yes.
Why is it 2t? Shouldn't it be 1?
Oh gosh. It was. I thought it was a 2. I was looking at the first one. Thank you. You're right. It's a 1/2. My bad. I was looking back at this one. That was the one I grabbed. That's 1. We had a good day though. Now, if it's just 1 at noon, that's great. Yes. That we're gonna find the distribution function. We haven't done it yet. This is how we find it. How we find it. Okay. Antiderivative for 1/2 t to the negative 1/2 is. Yeah, it's just t to the 1/2, right? Because the 2 and the 1/2 will cancel, and then 0 to x, and so we just get square root x, and we're done. Which again, remember, this only is true on the sample space, on the support, right? So again, if we were to graph this, I would graph square root of x up to 1. I would graph square root of x up to 1, but I would then say to the left, it's 0, because it doesn't start accumulating probability until you get to 0, and then we would keep it at 1 past 1. So it's a piecewise function in this case. Does that make sense? Now, if your support is minus infinity to infinity, I wouldn't have to worry about pieces together. Questions? Yes. I used a constant 1/2 because that was the constant we found. It's this part. That was the different part. That was part A. The c equal to 2 is for part A. The c equal to 1/2 was for part C, which is what I was doing. That's why. Questions on that? Other questions on that? All right, let's look at the next one here. What do we got? Things just got ugly, didn't they? All right. We've changed from nice functions. We had a line, we had a quadratic. Okay, then we went to some 1 over root x, and now we've got some thing with an x squared and an x cubed in it. Some monstrosity here. Okay. What is the probability that this regulator will last at least 7 years? Okay. Let's ignore everything else in that. Just what does the question ask me? The probability that what is true? Yeah, greater than or equal to 7, or strictly greater than 7, either or, it's going to give you the same answer, since we're in a continuous distribution. Now notice, before we do anything else, before we try to write this problem down or do anything else, look at my support. We're going from 0 to infinity. If I were just to write this down directly, you would do the integral from what to points? 7 to infinity, right? That's an improper integral. I prefer not to have to do that if I don't want to, if I don't have to, right? Okay. Can you rewrite this using the complement? Good. That's the complement, isn't it? And now writing the second part here, my integral goes from what to what? 0 to 7. And now I don't have an improper integral, right? We agree? Okay. This looks ugly. I agree, it looks terrible. Okay. But what technique, if you don't see how to directly integrate a function, what technique should you try? U sub, right? Looking at that function, what do you think you might want to let your u equal? Yeah, I probably might as well stick the negative sign in there as well. And to help me out, I'm just going to distribute the cubed over it. What's your du then? Oops, dx. Do I see a negative 3x squared over 7 cubed? Yeah, I told you it looked ugly, but there's your negative 3x squared over 7 cubed. Okay. Oops. Pardon me. All right. So the du will take care of the 3x squared, the 7 cubed out in front, and the minus sign, right? We're left with e to the u du. Let's change our limits as well. When you put in 0 for x, what do you get out for u? 0. When we put in 7 for x, what do you get out for u? Negative 1. Right? Now, only because we're so used to it, I'm going to flip my limits around. Why did I flip my limits around? Well, notice that my limit on top was bigger or smaller than my limit on bottom. So I just flipped it. And I flipped it and made it minus. You don't have to do that. You can just keep them the way they are. Antiderivative for e to the u. E to the u. E to the 0 is 1. So we get 1 minus e to the negative 1. So we just get e to the negative 1. That okay? Not too bad. That one wasn't a bad integral, was it? Kind of looked ugly to start with, but they made it nice for the u substitution. All right. Notice again, this is one of those problems that had you had the distribution function, you would have been able to just write it as 1 minus plugging in 7 into the distribution function, right? So let's see if we can figure out the distribution function and then do part B. Okay? All right. So again, our distribution function in our case will be the integral from 0 to x of 3t squared over 7 cubed e to the negative t over 7 cubed dt. We already did that integral a minute ago with a u substitution, didn't we? Right? We just did it a minute ago, didn't we? Okay. So I just rewrote it down. And now, if you put in 0 for, that should be a cubed. Put in 0 for t, you'll get a 1. And so then we'll just get a 1 minus negative x over 7 cubed. which is a nice form of it, isn't it? It's a lot easier to deal with, isn't it? Okay. Here was our u, right? Our du had a negative in it. That's where that negative sign's coming from. And all we're doing is integrating e to the u. All right. So let's see if we can use this to answer part B. Given that it has lasted 7 years, what's the conditional probability that it will last at least another 3.5 years? I'm going to rewrite my distribution function down here. Probability, it's a conditional probability again, right? Given that it has lasted at least 7 years, so what goes in the given part? Good. Given that it's lasted at least 7 years, what's the probability that it lasts another 3.5 years? What goes in this part? Good. Exactly right. So let's rewrite the conditional, simplify it a little bit, and then write it in terms of the CDF. How do we calculate a probability of a conditional again? Good. So we get the probability that x is greater than or equal to 10.5 and greater than or equal to 7 over greater than or equal to 7. How can you rewrite the top a little bit more simply? Good. The only way that you can be greater than or equal to 7 and greater than or equal to 10.5 at the same time is if you're greater than or equal to 10.5. That event is a subset of that event. So the intersection is just the smaller set. Tell me how to rewrite the numerator and the denominator in terms of the CDF.
P of x plus or f of 10.
Good.
1 minus f of 7.
Good. These are exactly the complements of, well, not quite exactly the complements of because of the overlap at the single point, but they're essentially the complements of the CDF, right? CDF is up until a certain point. This is everything past a certain point. They're complements of each other. Here is our CDF over here on the left side of the screen. Notice we'll get a 1 minus, right? So the top is just going to be e to the negative 10.5 over 7 cubed. The bottom will be e to the, oops, I put my negative in the wrong spot. Well, it's not wrong. It's just in a different spot. Negative 7 over 7 cubed. Ten halves over 7 is 1.5. It's 3 halves. 3 halves cubed is 27 over 8. And that's a 1, which is 8 over 8. So you should get e to the negative 19 over 8 when you're done. Assuming I did my arithmetic correctly. But notice that once I had the distribution function, it was a lot easier just to do the probabilities, right? So again, we're going to have a couple of big distributions that we're going to use a lot that will know what the distribution function is. So we'll end up writing the problems in terms of that distribution function. So that's why I'm emphasizing it now. All right. We'll do more of these on Thursday. I think you have homework due on Thursday as well, yes? Okay. Have a good one, and we will see you on Thursday, if not before.